In section 9.3, we prove the convergence of the alternating optimization algorithm. Here are the steps to prove the convergence. Consider the double supremum optimization problem in section 9.1. We first prove in general that if f is concave, then f sub k tends to f star. We then apply this sufficient condition to prove the convergence of the Blahut-Arimoto algorithm for computing C. The convergence of the Blahut-Arimoto algorithm for computing R ds minus S ds can be proved likewise. Section 9.3.1 is a sufficient condition for the algorithm to converge to the optimum. In the alternating optimization algorithm, we have UK plus 1 equals U1k plus 1, U2k plus 1, where U1k plus 1 is equal to C1 of U2k, and U2k plus 1 is equal to C2 of C1 of U2k, for k greater than or equal to 0. Define delta f of U to be f of C1 of U2 and C2 of C1 of U2 minus f of U1 and U2. This is the increment in f in one iteration if we start at the vector U. Then fk plus 1 minus fk is equal to f of uk plus 1 minus f of uk, where uk plus 1 is equal to C1 of U2k and C2 of C1 of U2k, and UK is equal to U1k and U2k, which is equal to delta f of UK. In lemma 9.4, we first prove that if f is concave, then the algorithm cannot be trapped at U if f of U is less than f star. Specifically, let f be concave. If fk is less than f star, then fk plus 1 is greater than fk. We now prove lemma 9.4. It suffices to prove that delta f of U is greater than 0 for any U in A such that f of U is less than f star. Then if fk is less than f star, we have fk plus 1 minus fk is equal to delta of f of uk, which is greater than 0, and this proves the lemma. To proceed, we first prove that if delta f of U is equal to 0, then U1 is equal to C1 of U2, and U2 is equal to C2 of U1. That is, the algorithm is trapped at U. Consider f of U1 and U2 upper bounded by f of C1 of U2 and U2, because U1 is updated to C1 of U2. This is further upper bounded by f of C1 of U2 and C2 of C1 of U2, because U2 is updated to C2 of C1 of U2. If delta f of U is equal to 0, then the inequalities 1 and 2 are both tight. Due to the uniqueness of C2 and C1, the inequality 2 is tight, then U1 is equal to C1 of U2. If the inequality 1 is tight, then U2 is equal to C2 of C1 of U2. But since C1 of U2 is equal to U1, C2 of C1 of U2 is equal to C2 of U1. Therefore, we have U1 is equal to C1 of U2, and U2 is equal to C2 of U1. This implies that if fk plus 1 minus fk is equal to delta of f of uk is equal to 0, then uk plus 1 is equal to uk. That is, the algorithm is trapped at uk. Second, consider any u in A such that f of u is less than f star. We prove by contradiction that delta f of u is greater than 0. Assume that delta f of u is equal to 0. In step 1, we have shown that u1 is equal to c1 of u2 and u2 is equal to c2 of u1. That is, u1 maximizes f for a fixed u2 and u2 maximizes f for a fixed u1. Since f of u is less than f star, there exists v in A such that f of u is less than f of v. This is shown in the figure with the x direction representing the u1 direction and the y direction representing the u2 direction. Let z tilde be a unit vector in the direction v minus u. z1 be a unit vector in the direction of v1 minus u1, 0, and z2 be a unit vector in the direction of 0, v2 minus u2. Then z tilde is equal to some linear combination of z1 and z2, written as alpha z1 plus alpha z2. Here, the actual values of alpha 1 and alpha 2 do not matter. Since f is continuous and has continuous partial derivatives, the directional derivative of f at u in the direction of z1 is given by the dot product of the gradient of f and z1. Now f attains its maximum value at u equals u1 and u2 when u2 is fixed. In particular, f attains its maximum value at u along the line passing through u1, u2, and v1, v2. Therefore, by considering this line, we see that gradient f dot z1 is equal to 0. Similarly, by considering the line passing through u1, u2, and u1, v2, we see that the gradient of f dot z2 is equal to 0. By considering the dot product between gradient of f and z tilde, we have gradient of f dot z tilde equals alpha 1 times gradient f dot z1 plus alpha 2 times gradient f dot z2, which is equal to 0 because both gradient f dot z1 and gradient f dot z2 are equal to 0. Since f is concave along the line passing through u and v, this implies that f of u is greater than or equal to f of v. This is a contradiction to the assumption that f of u is strictly less than f of v. Hence, delta f of u is strictly positive, and this proves the lemma. Although delta f of u is greater than 0 as long as f of u is less than f star, fk does not necessarily converge to f star because the increment in fk in each step may be arbitrarily small. Theorem 9.5 addresses this issue. It says that if f is concave, then fk tends to f star. Here is the proof of the theorem. Observe that fk necessarily converges, say, to f prime, because fk is non-decreasing and bounded from above. Hence, for any epsilon greater than 0 and all sufficiently large k, fk is between f prime minus epsilon and f prime. The range from f prime minus epsilon to f prime is illustrated. Let gamma be the minimum of delta f of u for all u in A prime, where A prime is the set of all u in A such that f of u is between f prime minus epsilon and f prime. Since f has continuous partial derivatives, delta f of u is a continuous function of u. The set A prime is compact, that is, closed and bounded, because it is the inverse image of a closed interval under a continuous function, and A is bounded. Therefore, gamma, which is the minimum of a continuous function of u over a compact set, exists. If f prime is less than f star, as illustrated, since f is concave, by lemma 9.4, delta f of u is greater than 0 for all u in A prime, and hence gamma is greater than 0. Since fk equals f of uk satisfies equation 1, uk is in the set A prime. Thus, for all sufficiently large k, fk plus 1 minus fk equals delta f of uk is greater than or equal to gamma. This means that once k is large and f of uk is in the range from f prime minus epsilon to f prime, the increment in each step is at least equal to gamma. Therefore, no matter how small gamma is, fk will eventually be greater than f prime, which is a contradiction to the assumption that fk tends to f prime. Hence, we have shown that fk tends to f star. In section 9.3.2, we discuss convergence to the channel capacity. The only thing that remains to be shown is the concavity of the function f(r)q. Consider a pair R1Q1 and a pair R2Q2 in the set A. Let lambda be between 0 and 1, and lambda bar be 1 minus lambda. An application of the log sum inequality gives the following inequality, where this expression is a mixture of R1 and R2, and this expression is a mixture of Q1 and Q2. On the right-hand side of this inequality, this lambda cancels with this lambda, and this lambda bar cancels with this lambda bar. Taking reciprocal in the logarithms yields the following inequality. Note the change in direction of the inequality. Multiplying by py given x and summing over all x and y, we conclude that f(r)q is concave. This completes the proof of the convergence of the Blahut-Arimoto algorithm for computing the channel capacity. The convergence of the Blahut-Arimoto algorithm for computing the rate distortion function can be proved similarly, and we leave the details as an exercise.